Statics is the physical science of how rigid bodies remain at rest under the action of external and internal forces. Take this industrial dump truck. To hold thousands of pounds of rock safely in an elevated position, every push and pull must perfectly balance out. The challenge for structural engineers is that real-world forces rarely act in simple straight lines. They operate on complex multidimensional planes, where raw physical analysis can quickly become difficult to track. To guarantee equilibrium, we translate loads into orthogonal components. We map the cylinder's angled force vector, resolving it into horizontal and vertical parts on a Cartesian grid. Acting at a distance from the hinge, it generates a rotational effect, a moment. Isolating these translational and rotational effects allows engineers to define the precise variables required to evaluate structural stability under load. To simplify mechanics, we use two geometric idealizations: the particle and the rigid body. A particle is an object possessing mass, but its physical size is negligible. A rigid body combines particles at fixed distances. Even under heavy load, these internal points never deform or shift. Assuming absolute rigidity allows us to apply the principle of transmissibility to analyze a body's external equilibrium. This principle states a force can be applied anywhere along its line of action without changing its external effect on the body's state of rest. While this simplification works for external equilibrium, it cannot be used to evaluate internal material stress. Shifting the point of application changes how forces propagate through the structure itself. This creates a fundamental distinction between external forces acting on the structure and internal forces acting within it. External forces are the actions applied to the body, such as the weight of the load or wind pressure, as well as the reactive forces from the supports keeping the structure static. Internal forces are the stresses distributed throughout the material as a consequence of those external loads. We classify stresses based on their effect. Tension pulls an object apart and causes it to lengthen. Compression squeezes an object, reducing its size. Shear occurs when unaligned forces push different parts of a body in opposite, parallel directions, forcing the material to cleanly slice or snap. Finally, torsion refers to the extreme internal twisting of an object, created when an applied torque or moment twists the material. Engineers map external forces to maintain the building's position, while calculating internal forces to ensure the material properties can withstand the resulting tension, shear, and torsion. To manage these calculations, we use Cartesian resolution to replace angled physical vectors with strictly orthogonal values. This 2D Cartesian plane shows an angled force, P. By defining the vector's geometric slope, the adjacent, opposite, and hypotenuse sides, we use similar triangles. We solve for horizontal and vertical components by scaling the total force against these geometric ratios. Analyzing structures in 3 dimensions requires a z-axis for depth. We calculate the bounding box's spatial diagonal using coordinates from all 3 axes. Each component maps to its specific axis through the ratio of its coordinate length to this total diagonal. This resolution provides a uniform method for analyzing spatial forces, reducing angled vectors to a set of manageable algebraic values, regardless of their orientation. Rotation is as critical as translation. The moment of a force is its ability to produce twisting about an axis, defined as force times distance. To track this, we assign clockwise rotation as a positive value. Mapping the true perpendicular distance from a rotational axis to an angled force vector across complex geometry is often mathematically cumbersome and difficult to visualize. We simplify this using Varignon's theorem, which states a force's moment is equivalent to the sum of the moments of its components. By resolving the angled force orthogonally, we use simple grid distances. The total rotational effect is the summation of these values. This also defines a couple, 2 parallel forces equal in magnitude but opposite in direction that produce pure rotation without any linear translation. By utilizing Varignon's theorem, structural engineers can calculate rotational effects strictly within a standardized coordinate system, bypassing the need for complex trigonometric distances. We can apply these principles to a rigid grid plate subjected to 2 angled forces, 60 newtons and 39 newtons. Our goal is to determine the total rotational effect about point A. First, we resolve each angled force into its x and y components. This aligns the pushes and pulls of the system directly with our coordinate grid. Next, we map the perpendicular distances from point A to the lines of action for these new components. Any component vector whose line of action passes directly through point A has a moment arm of 0 and contributes nothing to the rotation. Summing the remaining moments yields a final clockwise moment of 95 Newton meters. By splitting physical forces into a Cartesian grid, we decouple translational movement from rotational twisting. Quantifying these components and moments provides the mathematical data necessary to balance the system, ensuring the structure remains in perfect equilibrium.